right? You guys can hear me in the back, right? All right, cool. Hey guys, thanks everybody for first of all making it. It's really late in the night, right? Particularly the ones who have kids. I'm Manish, I'm the founder of Dgraph Labs and the author of Dgraph, the distributed graph database, and Badger, persistence key value library. And along with me is Carl McGuire, the Dgraph engineer who worked on Ristretto. Carl, if you can just quickly stand up and wave your hand if you have any hard questions. Carl will be the one taking them. I only take easy ones. Today I'm going to talk about how to build Ristretto. How many people here know Ristretto already? Okay, we got like 2 people. Oh my god, you guys don't read Hacker News. It's a high performance concurrent memory bound Go cache. Let's see. To build this cache, we looked at a fast cache in Java. Now, Go is built around simplicity and so on and so forth, and therefore it doesn't have as many libraries yet. Plus, it's actually like pretty young language. Java has an amazing library called Caffeine, which is a really fast Go cache, and there's multiple papers written about it and referenced by its author, Ben Mains. In process of writing this cache, we not only simplified some of the design aspects of Caffeine for easier code maintenance, but also researched ways to get similar kind of performance from Go by doing benchmarking, something that I think should be of interest to most Go users here today. In today's talk, I'll talk about why we chose to build Ristretto, and then go on to explain the various mechanisms that we use to achieve performance, some specific to the design of the cache itself, the design decisions for the cache, and some of them about the Go language. So, what's the main problem we're trying to address? Why build a cache? It all stems from the need to use a cache in Dgraph. We were using the LRU cache baked into Golang's root cache by putting a mutex lock on top of it. And we knew that maybe it's not the most optimal, but we would have never guessed how bad it would get. After 1 year of service, after 1 year of usage of the cache in Dgraph, we realized that removing that cache actually improved our query latency 5 to 10 times. And that was just mind-blowing, right? But in retrospect, it became pretty clear why that was the case. See, smart caches like LRU cache and others, they have to maintain metadata to ascertain what to kick out when the cache reaches capacity. If your cache never reaches capacity, it's all easy going. But generally, caches do reach capacity, and so at that time, every incoming key must displace some keys. Some key must go out, and to maintain the metadata for that kills the performance in a high high workload environment. So what happens is a get in a smart cache also becomes a write because it's writing to the metadata. And that means both getters and setters are all writes. Right? So logs must be acquired, which means that as the concurrency of the operations grow, the contention of these logs grow as well. It's an old thought, but let that sink in. Your cache could be slowing down your system, which is exactly the opposite of what you want. So let's put together the requirements for this Go cache, right? It must be concurrent, of course, right? It's Go. It must be memory bound because, hey, we don't have infinite memory. It must scale to the number of cores and Go routines as they're growing because Go is a language that lets you just spin out a Go routine by just putting a Go in front of it, right? So people do that. And it should also scale to non-random key accesses. Now, in a database, typically you would have a Zipfian key access pattern, which means that some keys would be accessed exponentially more times than other keys, right? So it should scale to that. And it should also have a high cache hit ratio. Just to explain, the hit ratio means that the request got served out of the cache. A miss means the cache could not serve the request, so it's a cache miss. And then a hit ratio means the number of total hits by total number of requests, which gives you hit ratio. You want a pretty high hit ratio, right, for your cache to be effective. We wrote about this maybe like 6-8 months ago, a blog post called State of Caching in Go, which describes these requirements and compares the available caches in Go language. I wouldn't go into details, but it was a popular blog post and it's a pretty good read, so do check it out. So what is this Ristretto thing? This is me trying to explain Ristretto to a barista. That's the reaction I get. It is also my favorite coffee. Wikipedia states that Ristretto, because there's actually like no real standard, everybody says something different. Wikipedia is the right one, right? It says that you take the normal amount of coffee ground, you extract with half the amount of water in the same time, and use a final product. That gives you the better part of espresso, which is Ristretto. If you're curious, you can try it out at Bluestone Lane in San Francisco, or use Nescafe Ristretto boards. They didn't pay me, I'm just a happy customer. So, the Go Ristretto is a high-performance concurrent memory Go cache. It has a high hit ratio, it has high read-write throughput, it scales the number of cores, and most importantly, it's contention proof. And that's the key. You don't want a cache to ever slow your code down. To quickly show you some code, over here, we create the cache by specifying how many counters you want. It's a least frequently used cache, so it is a concept of counters. The max cost of the cache, the buffer items, etc. You do a set in the cache, you do a get in the cache, you do a delete in the cache. It's just a cache. But voila, your code is faster now, perhaps. So, let's look into the various mechanisms which makes Ristretto fast. And we'll look at some throughput benchmarks towards the end if we have time. They're all available in public. The first thing is storage, which is where you store the data. So in Java, they have concurrent logless maps, right? But Go doesn't have that. Go only has a normal map, and you can put a mutex log around it. You can take that map and you can shard it, let's say 256 times, which is what we have done, and then put mutex logs around those, and then do some key distribution. Or you could try sync roadmap. How many people here have tried sync roadmap? No, very few people. I guess that people designed that way. I think Rockpack doesn't want you to use it. So if I say use it, don't tell him, right? So for storage, we did some benchmarks, right? And again, Zipfian distribution is what we are going for, which is no random key access. If you just do gets, so it's hard to do the mixed workload when we decide to abandon that benchmark. So we just do gets and we do sets. For gets, sync map is the fastest, right? Between sync map, sharded mutex map, and then mutex map, right? And then for sets, the sharded mutex map is the fastest. Now the important thing to notice here is that the sync map actually deteriorates really badly for writes. Right? So we decided not to use sync map because we want to make sure that across different kind of workloads, the storage would not become a problem. And so we chose to use 256 shards with the normal mutex-based program. So in Dgraph and Badger, we see keys which are quite long and can take considerable amount of memory to store, and we didn't want to pay for that cost. So what we did was we used a U64 hash over these keys and stored that in the maps. Right? We did some benchmarks against commonly, or at least known to us, hashing libraries. One of them was Farm Fingerprint, there is SIP, FNB, etc., and these are the benchmarks that we got from them. Then we came across, stumbled upon an approach which hooks into Go Runtime Memhash, which is used internally by Go Runtime. Right? And so this is the code that can let you use that. These are things that Go team does not want you to know. This should be like an and here's some ad to click on. Now, important thing to know about this memhash is that internally Go puts like a random number every time the process starts. So which means that the output from this hash would not be consistent or deterministic across multiple process runs. So it would be deterministic in this process. If you restart it, it would no longer be the same. But that's okay for a cache, right? It's not getting persistent. Now let's put that into the mix, and whoa, we got a hash of 64-byte key in under 10 nanoseconds. It's because memhash internally uses assembly code, right? And Go team is maintaining it, so great. Right? So that's what we're using for hash. Now there is a real issue here. People are like, hey, but 64-bit key is not sufficient. You could have collisions. So what we did is to run it twice and get sort of like 2 UNT64s to give us equivalent to 128-bit hash. And for collisions, if we had 820 billion keys in that cache, which is practically impossible, I think, you would get 10 to the power minus 15 probability of a collision. And fun fact, that's also the uncorrectable bit error rate for hard disk, so what can you do, right? I think at that point it just says good enough. So we, actually Carl is ready to fight anybody who says that 128 bit is not sufficient. And if you can prove to him, then he will increase it to 196. So let him know. Now, so far so good, right? Everything is clear. Feel free to ask any questions. I like it pretty interactive. So next comes concurrency, right? Ristretto aims to be contention proof. That means any metadata update has to be done in the background. It cannot be in the critical path of gets or sets or deletes. And all the gets and sets should come at a minimal overhead on top of storage access, right? You have to do storage access, right? Because if you want to do get return back, you must do the storage access. So storage access has to be done every time. But all we're trying to do is optimize for the metadata updates, in some sense. So for that, we look towards a paper called PP Wrapper, which introduces a system framework to make any replacement algorithm almost contention-free. The main concept there is batching. So instead of acquiring a mutex log for every metadata update, we fill up a ring buffer, and once it is filled, we drain it into the critical section. And this reduces the number of times you must acquire this global mutex log around the critical section, right? So ring buffer, drain, acquire a log, critical section, release the log. And by doing this, you amortize the cost of log acquisition. Now this batching system assumes that you must have a ring buffer which is fast and would not need a lock itself, right? Now, in Java, they have a thread local storage. In Go, you don't. So there are multiple ways to skin that game, right? One is to use a slice with a mutex lock in front of it to act like a ring buffer. Other is to use a channel, and channel internally has a lock. You don't see it, but there is lock inside. The third is to maybe use multiple channels or multiple slices and then do round robin across them, or you could do some sort of a random number. Both the round robin and the random would add their own overheads, which would be slower. On top of that, the other thing about the ring buffers is that they can be lossy, and that's important. Under heavy workload, the metadata updates for the getters and setters could be dropped to avoid contention. Again, this cache should never be the cause of contention, right? It should only make things faster, never slower. So we came up with a new mechanism to build lossy ring buffers using a Go data structure which does have access to thread local storage. Does anybody want to guess what that is? Sync.pool. Sync.pool automatically maintains many buffer stripes, and so what we're using it as is you can hand the user one of them on a get. After receiving one, the user knows that that user is the only owner, the only thing which has access to this buffer or stripe. So the key can be pushed into it without acquiring any further locks. And finally, the buffer can be pushed back into the single pool, right? And in a heavy workload, if there are too many buffers, the Go GC would automatically drop some of them, so we get the lossy behavior that we wanted, right? So it's a very simple code: sync.pool.get. You get this buffer.push, the key inside, sync.pool.put, the buffer back, and let's look at the benchmarks. Hey, so much better. So you can do it in 70.4 nanoseconds per operation. If you were to use mutex.log, you would get 210 nanoseconds per operation, and if you were to use channels, then you almost get a microsecond per operation. And all of these come with almost 100% pick ratio, at least in our benchmarks, there is almost like 0 drops. But obviously, I think when GC runs, some things will be true. Okay, I guess so far so good, right? Question?
How much jitter does GC add to this?
So in practice, so the question is how much jitter does GC add to this? Now I think during benchmarking, GC does not run if I understand correctly. So not much during benchmarking, but in practical systems when we run Ristretto, we see very little drops, to be honest. We don't see too many drops. So it's pretty effective. And it's also reflected in the hit ratios, which I'm going to talk about next. Yeah. Any other question? No? All right. So handling X, right? So the Ristretto config that you saw earlier, and if you have a great memory, you'll remember the entire config, right? You can specify how much buffer size you want in this. So if the buffer gets full, then all the keys in the buffer get pushed into a channel to update the counters. We haven't talked about the concept of counters, but we'll talk about it later. The channel itself is lossy, which means that if the channel has a capacity, assume it's 16 or something, or maybe 100. If you try to push and the channel is already full, then that buffer gets dropped on the floor. So that's a second level of lossiness. And that's how we handle the gets. So this can do a lot of bandwidth, a lot of throughput for gets. For sets, now sets in Ristretto go through a channel right now, which get processed by the admission policy. We will talk about the admission policy later. The lossy behavior and the admission policy does mean that sets can be dropped on the floor or rejected by the admission policy. So just because you did a set in the cache does not mean you will see it in the cache. And that's very different from almost any other cache that you would see, because LRU caches guarantee that whatever you just set would always be admitted. And that's not the case here, right? However, if the key is already present, then we'll definitely update it, because we don't want you to get back a stale value, right? So if the key is not present, you might or might not get it, but if the key is already present, you will definitely update the value. So, as we discussed, gets and sets metadata updates can be dropped on the floor to avoid contention, and however, this affects the hit ratio only slightly. Overall, still performing better than other caches. And so if you look over here, we went from 4 go routines to 64 go routines, 37% hit ratio in this benchmark went to 34%, which is just like 3% drop. If you look at every other cache, we have big cache, free cache, fast cache, go borrow, group cache. They're all pretty still below Ristretto. Okay. The other thing that we were not happy about was that many smart caches naively assume that each key value cost is 1. Ristretto allows setting a distinct cost to each key value pair, and it captures that internally in a key to cost map. So the total capacity of the cache is based upon that cost. So you could say that the cost is in bytes. You could say my cache should store 1 gigabyte of data, and if the value is 32, let's say, kilobytes, it could displace many smaller key values which might be of, let's say, 100 bytes or 200 bytes or 1 kilobyte, right? So the cache is aware. It gives you those kind of mechanisms. Now, let's look into the mechanism for how we maintain frequency counters and access and apply the policy. So Ristretto uses an LFU-based eviction policy. What's interesting is that Ristretto also uses this policy for admission. And as I mentioned, like Ristretto is unique in the sense that it does apply an admission policy. But by being judicious about what to admit, Ristretto does a better job at maintaining high hit ratios. So Ristretto uses this highly efficient way to track key to access frequency called tiny LFU. And tiny LFU is interesting because it provides a frequency counter which only takes 4 bits per key of storage in memory. So you can store 200 million keys frequency counters in 100 megabytes of data, right, in memory, which is pretty efficient. And in general, the more keys Ristretto knows about, the better policy decisions it can make, right? So if you in a perfect world, you would know about every key that you have ever accessed, and you'll be able to judge whether you should keep this key or you should remove this key, right? But we can't get there, so tiny LFU just gives you a much bigger window to look into. Now it also has a mechanism to halve the counters every n accesses, and n is something that you can control in the config, which means that it avoids the cache from getting bogged down by stale keys that you haven't seen for a while. So there is a recency window here. And it paves the way for more recently seen keys. Question?
Sorry, no.
Oh, okay. Finally, tiny LFU provides an estimate function, which is the frequency estimate for each key, right? So it has the increment, which is where you increment the counter, estimate, which is the estimate of what the counter for that key might be, and reset is the halving of the counters. In front of tiny LFU, Ristretto uses a bloom filter, and if the bloom filter is not already set, the key does not reach tiny LFU. It will only set the bloom filter. This way, the filter acts like a doorkeeper to tiny LFU to avoid a long tail of singly accessed keys from polluting the counters. So if the key only shows up exactly once in the entire lifetime, that key would never reach tiny LFU. And you can see over here, you have getter and setters, the keys are going to the doorkeeper bloom filter, and then if they pass through this, only then they will go to tiny LFU. So you deal with a lot of long tails. Okay, now that you understand some of the components, I can show you the overall architecture of the cache. Right? So the getter and setters are directly accessing the map storage, as I mentioned, because if you do a get, you better be checking, right? But while also pushing the keys over to doorkeeper, then to tiny LFU counters, then the policy, and the policy accesses the counters and the map storage to decide what to admit and what to evict. All clear so far? Yeah. Okay. All right. Let's look at the eviction policy. So, ideally, we talked about estimate, right? So we kind of have a sense for which key has a high frequency. In an LFU-based system, least frequently used system, you want to evict a key with a minimum estimate, right? But maintaining a priority list of all the keys with constantly changing estimates is kind of pretty expensive, right? So instead, what we do is Go maps come with a pseudo random access to the keys. So what we do is we iterate over Go map and we get 5 keys from there. Then we find the key with a minimum estimate out of these 5. And we'll get the minimum estimate from there, and we compare it against the incoming key's estimate. If the incoming key has a higher estimate than this key, then we will let the incoming key be stored. Otherwise, we will reject the incoming key. So we didn't have to look through the entire map. We just looked at 5. We picked the minimum out of them, compared it against the incoming. If the incoming is better, we accept it and evict the other one. Otherwise, we reject the incoming. And so that's admission and eviction. And if the cache is under capacity, then we just admit everything because hey, why not? So,
is 5 kind of an arbitrary value, or did you tune that at some point via benchmarking?
I think 5 was used based upon.
Enterprise like Redis, he ran his benchmarks and found 5 was pretty much close to theoretically optimal.
Oh, okay. So he asked basically how we came to 5 is the best sample size, and Antares from Redis, he has a blog post about this, and he found that 5, a sample size of 5 was pretty much, it was close to optimal, as opposed to just getting all of the, a really large sample size. So 5, we have the best throughput performance to the eviction rate that we have.
And also note that because the key values in Ristretto are not considered equals, a single key value could displace multiple key values, and so we have to make sure that it can still perform pretty well. And so that way, even when we're getting the sample, we try to be efficient about it. Okay, and this policy works pretty well and provides great hit ratios, better than almost any other co-cache, but still not as good as Caffeine. So there is something for us to aspire to. And we look at the benchmarks later. Now, you have seen the admission policy, you've seen the architecture generally. Let's talk about metrics. It's optional for you to turn it on or not, but I think it's important to understand whether the cache is doing a good job or not, right? So Ristretto allows you to use allows you to turn on these metrics, and what they do is internally they use atomic counters to track every time there's a hit, there's a miss, there's a drop, there's a rejection, so on and so forth, right? So there's a barrage of metrics that we track. Initially, we saw a big overhead to updating these atomic counters. And we narrowed the course down to false sharing. Consider a multi-core system where different atomic counters, 8 bytes each, fall in the same cache line. Now there's a way for you to get your cache lines. If you search online, there's a conf that you can get. So typically, at least on my machine, it's 64 bytes. Right? There's a cache line. So any update made to any of these counters which happen to fall in the same cache line would cause the others to be marked as invalid automatically, whether those counters were updated or not. That other core would have to force reload that counter with that cache line. Right? So let's say this is an 8-byte counter here, and this is an 8-byte counter here, and these happen to be the same cache line. 2 cores get it, one updates 1, the other core updates 2. The first update would invalidate the cache for core 1. So that means that's why there's contention. Now, what we can do is do some padding. We're trying to solve this by padding each counter with enough space to ensure that they fall in different cache lines. Right? So multiple cores can make progress, without any cache invalidation if their counter is not updated. Right? So in this case, let's say we split up the two counters in two different cache lines, 64 bytes each. Core 0 updates 1, core 1 updates 9, no invalidation, they both can progress concurrently. So this allows the statistics to be maintained with only 10% overhead on top of Ristretto. We did some benchmarks. If in the shared scenario, it takes 50 nanoseconds per operation. With padding, it takes like almost half of that. Now, all of the benchmarks and the code for Ristretto is available on GitHub. We have some time, right? Maybe you can show the benchmarks quickly.
3 minutes.
3 minutes, okay. All right, you guys can see it. Question?
I was curious how you figured out that cache line.
We got a lot of advice from Ben Mains. We got a lot of advice from Ben Mains. Ben Mains is the creator of Caffeine, so when we saw it, could get a sense that atomic counters were slow. Initially, we thought it could be because of Go, but then he had already seen this problem in Java, and that helped us narrow it down.
But you have precious little control over that in a compiled language, right?
Could you do that?
I said you have precious little control over that in a compiled language,
Yeah.
a high-level language.
Yeah, we don't. The question is do we have much control over that in a compiled language? I don't know actually if we have.
With assembler.
With the sender coding. Yeah, we should do that. Yeah, and maintain that code over time.
Right.
But if code team does it, then we can hook into it. So, any other question? Yes.
Speaking of anti-res, how do you stack up against
Redis? The question is, how do we stack up against Redis? Now, actually, I don't want to answer that question, but there is somebody else who has already tried putting Ristretto in a server and compared that against Redis. And according to this person's benchmarks, Ristretto outperforms Ristretto server. I guess it comes with a caveat that Redis expects you to run multiple different Redis processes in each server, and I don't think the benchmark has done that. It was just like one Redis server against one Ristretto server, so I don't know how that will play out. Yeah, but I always believe in concurrent programs than single-threaded programs, so I was never a big fan of Redis to begin with. One more question.
Just wanted to mention, you mentioned Memhash. It's going to be a package in Go 114.
Oh, cool.
Called hash/Memhash.
So there's a comment that the runtime.memhash function that we're using is going to be exposed to everybody as part of a package in Go 1.14, so that's great. Yeah. So, all right, it's a good time to plug in that Dgraph Labs is hiring Go engineers. We have built Dgraph, Badger, Ristretto, and we're building more. So if you like challenges, come join us. Finally, happy 10th anniversary Go. We love this language. Thanks to Carl, our engineer, who has been working on Ristretto over the last 6 months and building and maintaining it. And I would also like to extend special thanks to Ben Mains, who wrote Caffeine, and Damian Brisky for hit ratio benchmarks and just general help. Happy to take more questions. Yes?
Have you guys benchmarked what the difference is with the doorkeeper and without the doorkeeper?
The question is, did we benchmark with doorkeeper versus without doorkeeper? The doorkeeper concept came from the paper already, and it seemed logically to make sense to us because there is typically a long tail of only keys which are seen only once. So we just directly used it. Now the thing is, it's actually being used in the policy in the background thread as opposed to the critical path. So it shouldn't affect our performance numbers. It will only affect our hit ratios. So we decided to keep it as it is, as it was described in the paper. More questions? All right, one last question from me. So how many people are going to try out Ristretto tonight? All right, thanks guys.